Hey there, you're in love with your mate JJ. Today is Learning the Art of Electronics Day. Today is our first circuit for learning the art of electronics. We've already done an introductory video which came out a while ago now, and I've been trying to get this first lab done for some time. This will be, I think, the 5th time I've sat down to record this video. So hopefully this is the final cut and we get it shipped for Tuesday, which will be the day you're seeing it if everything goes to plan. So the silly job title for today is Operation Manager. Today I am the Operation Manager, and the operation we'll be managing is the first circuit in Learning the Art of Electronics, which is the hands-on lab course that we're working through at the moment. Of course, the course is supplemented by the textbook, which is The Art of Electronics from Horowitz and Hill. This is the 3rd edition. But we'll be working through the lab course, which is a separate volume, and this is the 2nd edition of this book. What we're doing today is Fig-1N.23, which I'll show you in a second. This exercise today is actually going to have 2 circuits in it. We'll make both the circuits on the same breadboard because one of them's just really an extension of the first one. So we'll do the first one, we'll do our tests, see how everything goes, then we'll add on the components we need for the second one, and we'll do our tests and we'll call it done. Before I take you over to the bench here to work through the book, I thought I'd pop you over to the computer and we'll go through the notes together. I'll tell you about that.
All right. Have we got audio? No audio. Oh, no, we've got audio. Okay, cool. I'll just take those off so I can see what's going on. All right. Here we are on the ITL wiki. This is the wiki for In the Lab with JJ, which is, of course, my YouTube channel. This is the home page. There's a note about news, which goes over here. And then there's the various projects that are being documented on the wiki. So the one we'll be working on today is Learning the Art of Electronics. So let's click on that. I've got a little bit of a blurb here about it and some links to other information. The subscriber only content is listed here. These are my book notes, and I'll show you those in just a second. But on this page, you will find the labs, and this is where we'll be documenting the labs as we go through them. So on the 1st of April, April Fool's Day this year, we introduced Learning the Art of Electronics. So we did our introductory video. The show notes for that are over here. And then we started to prepare for this, which is the next video. It'll be coming out on the 26th of August. So that might be when you're watching the video, if you're watching it on the day that it comes out. And we're doing, the chapter is DC circuits. And the circuit we're doing, or the circuits that we're doing, are from Fig-1N.23. We'll get the details of that in a second. So after we finish recording this video, I'll upload it, and the link will go here, and the show notes will go here. The reading tells you in advance what reading to do for the next project. So the project today will be 1N.23. And if you want to do the reading, if you've got yourself a copy of the book, and I'd certainly encourage you to get yourself a copy of the book, you should read up to page 17. Read up to page 17, and that's all of the reading that we need to do as preliminary work for the circuits that we'll be constructing today. I'll show you my notes about the first couple of pages in the book, or the first 17 pages in the book. I'll show you those in just a second. I've got those notes over here if we click on this link. This other section, by the way, this extra reading section, this is just me making some notes about references from the coursework to the other books. And the other books are Electricity and Magnetism, Principles of Electronic Circuits, and of course the Art of Electronics. So there's 3 different books there that are extra reading that you might like to do in advance of the work that we're doing today. So feel free to press pause, go and read Learning the Art of Electronics up to page 17, and if you've got the other texts, Electricity and Magnetism, Principles of Electronic Circuits, or Art of Electronics, go and have a read of the bits and pieces. The first 2 chapters of E&M, chapter 1 of POEC, and the appendix A. It's a mathematics appendix in Art of Electronics, and chapter 1. That was a lot to talk about. So I might as well just pop you over here. This is the book notes for Learning the Art of Electronics second edition, which is what we'll be looking at today. You can see these notes here. They're subscriber only material. So if you want access to these notes, please support me on Patreon, and I'll set you up with an account. You don't need access to these, particularly if you get yourself a copy of the book. That will be best. But I will run you through some of my notes, and we'll get ready to do the circuit, or the 2 circuits that we'll be doing today. So we start off in part 1, which is analog passive devices, and the chapter we'll be doing today is DC circuits. It's lab 1, or chapter 1. So I'll just call out the stuff. I've got lots of details in here, but the really rudimentary stuff is highlighted in green, so I'll just run you through that. What we're doing today is we're going to learn how to make a voltage divider. The subject of this course is the laws, rules of thumb, and tricks that constitute the art of electronics as we see it, as the authors see it. When we deliver power to something, that something is called a load. This course isn't really about powering things. It's about this course is concerned with using electronics to model and process information. And it asks the question, is it better to model information with a voltage or a current? And you can think about that if you'd like to think about that. Or the answer is basically voltage is better, because current requires energy, whereas voltage doesn't necessarily need much energy at all. Or, yeah. So, by the way, I believe that a bipolar junction transistor, a BJT, needs a current on the base, whereas like a FET, a field effect transistor, they only need a voltage. I think that's the difference between these two, but we'll learn more about that as we go. Of course, Ohm's law, we need to know Ohm's law for this work pretty much straight away. V equals IR, where V is voltage in volt, I is current in amps, and R is resistance in ohms. I thought this was good. I mean, it's trite, but a volt is what pushes an amp through an ohm. I thought that was pretty good. A volt is what pushes an amp through an ohm. 1 volt is the work done as one adds 1 joule of potential energy to 1 coulomb of charge. It's just another way of saying the same thing. Ohm's law is useful, but it only applies to resistors, so you shouldn't expect to apply it where it doesn't fit. The inverse of resistance is conductance. So in this case, G. What did I do? What did I do? I've just clicked through on something. Oh, I see. Yeah, there, conductance. Oh, I'm not sure what I did. Anyway, yeah, the resistance. So the conductance is G, and of course it's in Siemens or Siemens. I'm not sure how to pronounce that exactly. Conductivity degrades, increasing resistance when temperature increases. That's a general rule. That's usually what happens. There are some exceptions. Various strategies for making a resistor: carbon composition, carbon film, metal film, and wire wound. Many electronic components do not obey Ohm's law, so just be aware of that. In fact, a lot of them don't. Don't expect to use Ohm's law where it doesn't fit. It only works for resistors. We can extend the reach of Ohm's law with dynamic resistance. So the dynamic resistance is the change in voltage over the change in current, which is basically the tangent to this curve. And this curve, by the way, it's usually I against V, but they switched the axes around so that the tangent is in ohms. Anyway, there you go. Power is the rate of doing work. Components will have power ratings. Formula for power in watts: P equals IV, or P equals I squared R, or P equals V squared divided by R. To find the minimum resistance for a 1/4 watt resistor at 15 volts, We put 1/4 watt equals 15 squared on R min, so we can express R min as 225 divided by 1/4, which is 900. So that's roughly 1 kilo ohm as the minimum safe value at 15 volts. There you go. Because anything else would require more power than the 1/4 watt. Current measures charge per unit time, and voltage measures work per unit charge. So the charges cancel, and IV equals work times charge on charge and time, which equals work on time, which is power. Power in watts. In this course, we rarely worry about power. There we go. All right, so there's two laws from Kirchhoff. There's Kirchhoff's voltage law, which is the sum of voltages around a loop is zero. So they all go around to zero. And the current law is that the sum of currents in equals the sum of the currents, the sum of the currents in and out of a node is zero. And they say, of course, that's the algebraic sum. So if the sign will indicate the direction. So we can see applications of these laws. For series current, the total current is the same as I1 and I2. Parallel current, the total current is the current through 1 and the current through 2. The series voltage, the total voltage is voltage 1 plus voltage 2, and in parallel, the voltage is the same, voltage and voltage 1. And then this is the diagram relating to these arrangements. They show you how this is actually a circuit if you bring the ground back around to the power supply. So you've got to bring that knowledge that this is actually a circuit to the drawing, because it's not necessarily obvious, but it should be obvious to you, and you do need to understand this. So with parallel resistors, the conductances add, which is the reciprocal of the resistances, which is easy. Well, it's, yeah, anyway. Oh, yeah, okay, and this just talks about how the things break down. When you've got equal R, then it's a half of R. When you've got 1R and 10R, then you've got 91R. And similarly over here, you get 2/3 of R if you've got 2 out of 3, like this. I liked this one. This says that this is small r and large r, and in parallel, it's the small r that dominates, and in series, it's the large r that dominates. So that's good to know. Here's our rule of thumb there we go. That's this here in words. So in a parallel circuit, a resistor much smaller than others dominates, and in series, the larger resistor dominates. Fair enough. When using a potentiometer as a variable resistor, it's a good idea to tie one end to the wiper. And that's explained in the book. I forget the deep justification for that, actually. I think it might have been a safety thing in case it comes loose or something. I forget. But feel free. It's chapter 1N3, first application voltage divider. There'll be more notes about that in the book. Now you see here, these diagrams which I've been doing, these are done in KiCad. And it has this nifty feature where it puts in these bits and pieces that it calculates. So it figures out that that there's 150 milliamps, 1.5 milliamps flowing through this circuit just based on the voltage, and it knows these resistances. So I thought that was pretty cool, and this is sort of what we'll be investigating today. This is, of course, just a voltage divider, and associated with this was the first method to calculate the voltage through these resistances, and that's all the mathematics for that there. And this is the same thing again, and eventually we get down to I'm just going a bit too fast, aren't This formula here, V out, this is a voltage divider, and V out over here equals Vn over here times R2 here divided by R1 plus R2. So that's this expression here, 1n1. So apparently we'll use this expression fairly often. It's good to know. And okay, and then the way they suggest that you muddle through this in your head is to say it to yourself out loud. So say, since the currents in the top and bottom are equal, that's here and here, the voltage drops are proportional to the resistances, which are here and here. And later we will call these resistances impedances, which is a more general notion that covers devices other than resistors. So in this case, where the low resistance makes up half the resistance, it will show half the total voltage. And then there's some other examples given here. Now this is a loaded voltage divider. So this is where someone's coming along and attached a load, and we'll be looking at that again later on. I don't think we're looking at it today, but we will be looking at it soon. The question is, so this is where you do it sort of manually, and this is where you apply Thevenin shortcut, and you take the bottom network of resistors. Oh no, that's not right. Hang on. Yep. Here we go. All right. So you can calculate the Thevenin voltage and the Thevenin resistance, which is R1 in parallel with R2. And the voltage here is, as we saw earlier with our expression, V in R2 on R1 plus R2. So that's the expression for the Thevenin voltage, and the resistance is just these two resistors in parallel. So here we've got a general definition and procedure for determining impedance at a point. To discover the impedance at a point, apply a delta V and find a delta I. The quotient is the impedance. So that's the same thing as an example here, where you've got 1 volt divided by 0.2 milliamps equals 5 kilo ohms. And have we finally landed? We have. This is the circuit that we'll be doing today. So that's my notes in the book so far, up to figure 1N23. We're going to go over to the bench and we're going to make this circuit and we're going to test it and see how it behaves. And then once that's done, we'll extend the one that we made to put on this little extra bit over here. And we'll do some more testing to get some more results. I won't be able to provide 20 volts because my bench power supplies only go up to like 19.5 volts, so I just can't quite do 20. So we're going to do all of this at 10 volts. We'll keep the resistances the same. So the resistances will be 10k and the voltage will be 10 volts. Except over here where it will be not 11 volts here, but 6 volts here. That's the way I'm planning to do that. And we'll get measurements at all of these points for the voltage we'll get the voltage across these various components, and we'll get the current through various points. So that's what the video will be today. So I think that is everything about the notes. So what we'll do is we'll pop over to the bench and let's build one of these circuits. Here on the bench. So I've got our little circuit board that we'll be using. That's there, and these are the power in sockets that we'll be using. The power cables we made recently. I did an electronics project where I built these cables. We'll plug these banana plugs into the power supplies up the back there, and we'll plug these, this end into these, which will be soldered in there. I need to fire up the soldering iron, the power supplies. So that all looks pretty well and good. I need something else. What do I need? We need our resistors and I need a wire. So let me just go and grab some stuff. All right, I'm back and I got these. This is a drawer full of 10K resistors, and this is a container full of breadboard wire, which I've discovered is my preferred type of wire for these types of projects. I don't think we're going to be needing the old wire strippers there today, so we'll just put those away. Now, we will need trusty multimeter, but only one of them, I think. And we're probably going to want to put put the book up for reference. Is that going to work? Oh, looks like it'll work. So, can you see that? No, but you don't need to see it. I'll show you what we're doing, and then we'll do it. So, this is the book, and this is page 17. So you should read up to page 17 if you're going to follow along. You can pause the video. I'm going to do that now. What we'll be building is the voltage divider that's shown here with 10K and 10K. So it's two resistors. We've got voltage in, half the current, half the voltage goes across here, and the other half the voltage goes across here. And there is no load. So we'll be doing that first, and then once that's done, we're going to add this wiggle voltage with the extra 1 volt, and just see how that affects things. Yes. So you don't need to see all of this. I will write it up. What's happening here? All right. Can you see it? No, you can't. Okay. We're going to come back to that multimeter. I'm going to do today is get some room for our notes. We're going to be making notes over here. This is learning the art of electronics, 1N23, and the date today is the 23rd of the 8th, not 05. Gee, can't take me anywhere. Yes. 23rd of the 8th, 2025. All right, and the circuit that we'll be doing is we're going to take 10 volts and run it in here through R1, 10K, and then down here, and then R2, 10K, and then that's the ground. And out here is V out, but we won't be using V out here today. So we're going to label this point here, we're going to call it A, and then this point, say here, we're going to call that B. We're ignoring that wire, it's not being used. And then we're going to label the point down here as C. C down the bottom here. We'll be testing various things. So we're going to want to get the voltage across, voltage at A and B, and then voltage at B to C, and also the voltage from A to C. that'll be the whole voltage across the whole circuit, which will be 10 volts. But we'll check all of these figures. Then we want to get the current through A, and we want to get the current through B, and we want to get the current through C. And that will be all of the measurements that we'll need to take. We'll be able to take the measurements one at a time with our multimeter when we're ready to go. So this is the circuit board we'll be using. I'm going to let's put some water in my soldering iron sponge. We're going to be using some of these, which are pin headers across the top here. We're going to be putting in the power as well. We'll do the second power. We'll do that later. The one we're doing now is this one. So let's get started with the old power in. We're going to need some solder. Some solder here. All right, so let's put the power supply in first. I might actually even just get myself some magnifying. These are my magnifying glasses. They just help me see things up close. So see if we can use those. Yeah, that's good. Very good. All right. So here's our solder. All right. All right, that's going pretty well. I think at this point we'll just time lapse. So I'm going to time lapse the construction of this board, and I'll report back when that's finished. All right. So there's our little circuit put together. This is only the first part. The extra bit will go on later. Power supply in here. Each point on the circuit gets 4 pins on the header. So point A is green, point B is yellow, and point C is white. The 10K resistors join each of the points. We can use the outer 2 pins for voltage measurements and the inner 2 pins for current measurements. Now the only thing that's missing on this board for testing now is a label. So I'll just I'll make a label quickly. All right, so I've labeled it here. Can you see that? LAOE 1N23, and the T2 is for take 2. It's actually take 3. This is the one I did the other day. This is the one we did today. And before that even was this one, which I salvaged the bits off actually. So this was the first one. It was an abortion. This one worked okay, but we had another go at it today, and that's this one here. So a little bit of behind the scenes there for you. So we've now got our circuit assembled. It's time for us to take our measurements and see how the circuit behaves. Of course, it's a voltage divider. We're putting 10 volts in. The R1 and R2 are equal, which means that 50% of the voltage will go through here and 50% of the voltage will go through here. So V out will see 50% of the voltage. So there won't be anything surprising there. The current will be the same everywhere. And that's what we should see. So let's do our voltage readings first. So what are we going to do? I need to get rid of this. Hang on a sec. I'll be 1 second. I'll be right back. Thought I might throw you over here while we're setting up. I've just got that book. It's getting in the way of my power supply usage. So, and I put the notes over here. You couldn't see them there anyway. So these can stay there. That's all very good. And we can get rid of this guy. We won't be needing him. Like I lost the remote control there. See if I can get that back. All right. Now, got our power supplies. That's all well and good. Can I show you? Let's try. What are we going to do? I'll just pause for a sec. I'll be right back. You can't tell, but today is the next day. I just missed a whole day recording. I went to use my power supplies over there, and I wanted to show you them as I did that, and then I discovered that the software I'd been using called Elgato Epoch Cam, I believe, has gone obsolete. It's not available anymore. So it stopped working for me, and I needed to find another solution. So I found something called Droid Cam, and I'm using that now. So long story short, I can now show you the power supplies. And this is them. So up the back there, I've got two power supplies. Top one is supply 1, bottom one is supply 2. They're Ryden RD6006 power supplies. They've got 19.9 volts in. The top one's got 19.92 volts and the bottom one's got 19.97 volts. So call it nearly 20 volts in, but we can't do 20 volts because it's a buck converter and it can only convert down. It can't convert up. So the values we have essentially are 19 volts or less, which is good. Should be fine. According to the textbook, they don't tend to use more than 20 volts. Sorry, more than 15 volts. The example for this thing says 20 volts. We're not going to be able to do that, so we're going to halve everything. And where it says 20, we're going to give it 10. And where it says 11, we're going to give it 6. And we'll do that together now. We've got our circuit made, so it's all ready to go. I wonder if I can... let's just see. Yeah, there we go. All right, so I'm going to transition you over to this view, which has got up the back here a view on the power supplies. So you can keep an eye on that as we wire up our power. So we're going to want positive on the right and negative on the left, and then we're going to power in over here on the circuit. We'll put our power in on our power rails. So that's all wired up now. Oh, and we'll get our notes. We did this yesterday, so you've already seen this. This is the circuit that we're testing, and these are various points A, B, and C that we're interested in. We've got 10 volts in and 10K resistors. So
we should be able to get voltage readings and current readings using our little jig here. So let me just clean up a bit of the mess. We've got a solder up the back there. We're going to need a multimeter, and we're going to need a multimeter with some male jumpers on it. So let's use our EV blog meter. I had a problem with my EV blog meter the other day, and happily it was user error. I did the wrong thing. I didn't know how to use it properly. But I spoke to my mate Dave Jones over on the EV blog, and he very helpfully set me straight, figure out how to use the equipment. The problem I was having was that my current mode was set to AC, and of course I'm not using AC, so that was a bit of a problem. Now, what we're doing now is not AC either, and it's also not current, it's voltage. So let's put this thing on DC voltage, and it's on auto DC, very good. So, oh no, I've got it wrong. I thought that we needed male pin headers, but we don't. We need female headers. So it's male on the board, so female. There's the standard DuPont female there. We all know and love. So let's get ready for that. Now we're going to be doing. Can you see that? Yeah, you can. Good. So we're going to be doing point A, AB, and then BC, and then AC. So let's do AB. So this is A, and this is B. All right, now we're going to turn it on. Well, first of all, we'll make sure we're set correctly, and we're not. So we need voltage set 10 volts, and current set. It's constant voltage, so this current matter doesn't matter much. Over voltage is at 20, so we're basically set at 10 volts. Over voltage is 20 volts. The current over current is 1 amp. We won't be drawing 1 amp. So we're good to turn that on. On we go. And this circuit is drawing pretty much zero current. We're not doing a current reading. We're doing a voltage reading. So, yeah, okay. So VAB is 4.983 volts. Very good. Now the next reading we're going to do is B to C. So we'll turn him off, and we'll do B to C, turn him on, and B to C is 5.025 volts. And if we do VAC, that is 10.01. It's jumping around a little bit. 10.01. All right. Now we're going to be doing the current next. So we'll turn the power supply off. We'll change our probe situation. We're going to be measuring microamps. It's beeping at me. Yep. There we go. And in order to do the current reading, we have to intercept the point. So that's what these jumpers are for. So we're going to take off the green jumper, and we're going to short it out with the multimeter. All right. So now we should be able to see a little bit of current going through there when we turn it on. On he goes. All right. Oh, now this is the traps for young players. You see so I'll just turn the power off. You saw it gave a 0 reading because it's in AC mode. So we should be able to hit, what, is it level? No. Okay, select then. Yeah, there we go. Oh, okay, cool. So I'm not sure what the level does. I pressed it a few times. Not sure. Anyway, it's on voltage DC now. So let's throw him back on. All right. And it says that it's drawing 0.5 milliamps. So let's try putting him over into microcurrent mode. That's 500.7 microamps. That's such a low reading that the power supplies up the back here register it as 0. So IA is 500.7 microamps. So we'll turn him off and we'll set it up for the current through B. Okay, and on we go. And the current through B is 0. Is that what we're expecting to see? Oh dear. Huh? There we go. All right. The current. I had the reason I was getting reading. I plugged the plugs in wrong, so I fixed that, and now we're seeing something. So that explains that. Thought maybe I was going potty. And the current through C. So we'll turn him off again. Take him off there. All right. Of course, it should be the same everywhere, the current, which is why I was so confused when we saw 0. And there we go. That's 506. 500.6, that is. 0.7 then. Microamps. All right. So, that concludes this part of the experiment. So we've drawn up this circuit. We've measured the things. So we see the voltage across AB is 5 volts, and across BC is 5 volts, give or take a little wiggle room. The voltage across the whole thing is 10 volts. The current through each part of the circuit is 500 microamps. So what we're ready to do now is the second part of the circuit. So I'm going to take a break. I'm going to come back and then we'll mod this circuit board so that we can do the rest of the circuit. So I'll be back in just 2 secs. All right, I'm back. So I thought I'd just remind you about the circuit that we're doing. Can you see that? I think you can. Great. So up the top here, we're going to be adding this voltage source in the bottom here. So we're going to need a circuit board for that. And I forgot to turn this off earlier. So just unplug him for now. And when we plug it back in later, we're going to need 2 power supplies. So I'm going to put another one down there. So I'll make sure the soldering iron's on because we're going to need to do a little bit of soldering. And a little bit of water for the soldering iron. So have I got a... Yep, I'm just looking for a little power connector. I've got one out already. Very good. Just warm up the old soldering iron. Now, you need a bit of solder. Let's put the power in first.
I got my just gonna get my old goggles. These things are magnifying glasses. All right, well, that's all well and good. I suppose I should just time-lapse this. So I'm going to finish off the circuit. I'll be back when it's done. All right, so there's our circuit done. We've just wired in an extra power supply over here that runs through this point here, which we're going to label D probably, and that runs through D and then into the middle terminal here, which is B. I've put it on the right-hand side of the terminal, which will only matter if we're measuring current, of course. So that's our circuit ready to go. Now the next thing to do is testing. I'm going to be disappearing just for a quick second. We'll come back and we'll do the plan for the testing, which is coming up next. All right, so on we go. I just washed my hands. I like to do that after I've been handling leaded solder. We won't need these. I'll put those away and be. All right, so we're going to turn the page. And we're going to draw the second circuit. So it's a new date today. What's the date today? I might try and give my pencil a bit of a sharpen. Does it come with a sharpener? I'm not sure. Oh, yep, there's a sharpener in that end. Just give me 1 sec. I have to say, I'm very happy with this mechanical pencil. It's really kick-ass. Look at that. It's got a little sharpener in the end, so I sharpen up that point. Very good. Now, today is the 25th of August 2025, and we are working on learning the art of electronics 1N.23, and we're going to have 10 volts in. We're going to send it through R1, which is 10K, and then we're going to send it through R2. Let me fix that. Dyslexic John. I always write things down wrong. R2 10K, and then down here to ground. We're going to call these various points A and B and C. C is also ground, mind you. And we're going to come out here. Let's come all the way out here. And we're going to put in another supply, and that's going to be 6 volts. And we're going to have a point here called D. And then we're going to run him out down to ground, which is also C. All right. So, what are we interested in? We want to know about the voltage AB. V, A, B, and then we're going to do V, B, C, and we want to see, let's just say VB, oh, that was VBC. Yeah, that's all we want to see there. We could see the whole thing, so we'll see V, A, C. So that does us for voltages. B and D for voltages purposes are the same point. So Now let's do current. We'll get the current through A, and we'll get the current through C. Oh, I didn't leave myself any space. The current through A and the current through C, and we want the current through D as well. So let's put our multimeter in. Where's my? You know what I've done with my bookmark. Leave him open over here. Put our multimeter where we can see him. We'll turn him on to voltage mode. There we go. And that's DC voltage. That's good. Oh, we're going to need to power this thing. So as you can see at the back here, we've got our power wires. So we've got power at the bottom and power at the top. So, this is, why is that on VSET? I don't know. So we'll put the negative on this side and the positive on this side. And we want to set it at 6 volts. And it's already set at 6 volts from earlier. And the current's at 5 amps, but it's not in constant current mode. Anyway. Over voltage is 20 volts, that's fine. And over current, we might as well just put it at 1 amp. Shouldn't draw much current. So we're on 6 volts basically. That's what we need to know from this. And we're going to run our 6 volts into the bottom end of our circuit. So that's 6 volts in the bottom there, and this is 10 volts on the top. Nothing's turned on at the moment. Let's change that. Let's turn everything on. So power at 6 volts, power at 10 volts. So if we want to get the point AB, we can go here and here. And our voltage for AB is 4 volts. Let's say 4.005 volts. And if we want BC, we'll do that like this. And that is 6 volts, 6.009 volts. And then the voltage between A and C is 10.02, 10.01, 10.01. All right. So now it's time to do some current readings. So we'll turn off our thing. We'll put this in current mode. We'll disconnect it here. We'll turn our power supplies off. We'll take out the, what do we want the current through A? So let's get ready for the current through A. We have A and A. That's the current through A. So we'll turn our voltages on, put our thing in microamp mode, and we're reading 400.6 IA, 400.7 then microamps. So now we want to do the current through C. I'm going to do the current through C. A, B, C. This is C. All right, so let's power everything up. And we've got current through C, 595.5 microamps, 595.5. And we want to see the current through D, which is this point here. So let's turn off our power supplies and let's put ourselves in current mode over here.
All right, so let's power everything up. Power on the bottom, power on the top, and we're looking at 192.7, 192.7 microamps through D. And that is all of the readings that we're interested in. So we can turn off our power supplies. Very good. We can disconnect our multimeter. We don't need him anymore. We're finished. So let's talk about the readings that we got. So what did we see? We've got an extra 6 volts in here, which accounted for the current through D. And of course, the current through A and the current through D summed to the current through C. The current through C by the same would have been the same as B if B was drawn on that side of the line there. So actually, I'm not sure about that. No, B and C. I'm not sure. Maybe we should have just done the measurement, but then we would have to know. Anyway, okay. So what am I trying to tell you? The current through A is 400, and the current through D is 200. So 200 plus 400 is 600 down here. That's what we're looking at. The reason why this doesn't add up is because of this. This is actually providing extra current, which turns up down here in C. It's not there in A. The voltage, the supply voltage disparity means that the resistors, even though they're the same, doesn't lead to the same voltage. You can see that the 6 volts here means that this is only 4 volts because 6 volts, the potential difference between here and here, because here is at 6 volts, is 4 volts. So that's what we see there. Voltage AB is 4 volts. Voltage BC is 6 volts, and the voltage AC, oh, that's not right. Is that what we want? Oh yeah, voltage AC, 10 volts total. Why didn't we do B? Yeah, okay. Because B is the same as D for voltage purposes. Okay, so we've got 4 volts through here, 6 volts through here, and I guess 6 volts this way. Yeah, right. So BC and DC and DC, they're all, remember this point and this point are actually connected to each other. They're the same. Okay, and similarly we see different currents distributing in the same ratio. So we've got through A we've got 400 microamps, through C we've got 600 microamps, and through D we've got the extra 200 microamps, which adds to create C. So at last we've finished the first lab exercise for learning out of electronics. I'll throw you over the farewell cam and we'll wrap up. Before I take you over to the farewell cam, I just wanted to just clarify one thing, which is pretty important part of what we're learning here about electronics. The idea with this voltage here was to add a delta V, and the delta V equals 1 volt. So and we added, because it was this point was 5 volts, and we've added 6 volts, so that the delta V is 1 volt, and we wanted to compute a delta D or current, delta current.
and we calculated that with we measured that using the current probe, and that equals 0.0001927, which means that the resistance that we're seeing, which is this R1 in parallel with R2, which is the Thevenin voltage, is 5K. So this is the 5K that this circuit, the Thevenin model of this circuit has 5K coming out here, and that's what we get when we go resistance equals delta V divided by delta I. We get R equals 1 divided by, and then 0.0001927 equals 5,189, which is pretty much 5K. So that was the experiment, was to provide the delta V, one wiggle volt of 1 volt. We just bumped it up from 5 volts, which it already had, to 6 volts with the extra 1 volt. Then we measured the current through D, and we got this reading. And then the dynamic resistance, or the Thevenin resistance, we calculated it like this. We got this value 5K, which agrees with the model. So I hope that's clear. I'm still trying to get my head around all of this too. If you have any questions, just hit me up in the comments and we'll try and muddle through. But I think part of what they wanted you to understand here is that that you can actually compute the Thevenin resistance sort of empirically with doing the delta V and delta I equation, as well as just dead set measuring it with the multimeter. So yes, that concludes this video. So I'll throw over to the farewell cam and we'll wrap up.
That's a wrap. How exciting, huh? So we did our first circuit for learning the art of electronics. We've seen the results. We're getting our head around how voltage dividers work, and we're also learning about the Thevenin equivalent circuit with the Thevenin voltage and the Thevenin resistance. In this case, we had two 10K resistors. They created a Thevenin resistance of 5K, yeah, that's everything for this video. So there'll be more coming out soon, hopefully next Tuesday. That's my goal. I haven't recorded that video yet, but I'll get right on with it. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.